Okay. So essentially what this is this is the area under the heat capacity curve from 0 Kelvin to the temp of interest. And so what that means is you have to collect data to very low temperatures. And so what they do is they'll collect data, they'll measure heat capacities at extremely low temperatures and then extrapolate the curve to 0 here. Obviously they aren't going to get any data here. Then we saw these jumps here. And so by doing this, let's say I'm interested in 298 Kelvin. So here I'm at 298 Kelvin. I want to figure that entropy out, and then I'll integrate. That is, I'll take the area under this curve here.
And you're just taking the differential to be dt?
Mm-hmm. Right. This, yeah, you don't, I mean, if you want to see this, scroll down to the bottom of the page, and there's a little box there if you want to see. It's not difficult. The actual calculus of it isn't difficult. But, yeah, there would be a little heat here, but essentially we're just looking at the heat capacities of temperatures. We'll leave that off for the non-calculus people. And so you don't have to have calculus for this class. And likewise, as long as we have data out here for the heat capacities, we can determine the entropy, the absolute entropy at any temperature. Right? And so we can get the absolute entropy at any temperature, basically. Well, that's a lot of data. That's a lot of entropies, right? A lot of entropies. Too many. Because, do you really want to know the entropy at minus 43 degrees C for water? Well, it's probably not that useful. But what would be the most useful? If you were going to have one, let's say one temperature, what would be the most useful temperature? 25 degrees Celsius would be the most useful temperature. And so the entropies, absolute entropies, at 25 degrees C are compiled in Appendix D. Well, is 25 degrees C what we call the standard temperature, standard thermodynamic temperature? Unfortunately, it's not, because if you call 25 degrees C the standard temperature, a lot of people don't like reactions at 25 degrees C because a lot of reactions at 25 degrees C are just too slow. And so what they like to do is they like to heat them up, to warm them up so that they go faster, right? And so we do a lot of chemical reactions at various temperatures. And so there isn't a fixed one, but if you're going to pick a temperature, you might as well pick room temperature, for that. Well, what if we're doing a reaction at a different temperature? What if, then we need the entropy at that different temperature, right? Well, there are other tables, of course, that we could look that stuff up. But let's take a look at Appendix D to get familiar with this table. You guys have used Appendix D, right? You've used this first column of Appendix D. The first column of Appendix D is calculating delta H of reaction. Delta H of reaction is equal to the sum of the delta H's of formation of the products minus the sum of the delta H's of formation of the reactants. So when we calculate delta H, we aren't actually using absolute enthalpies, we're actually using delta H's to calculate a delta H. Right? But for entropies, we're just going to take the entropies of the products minus the entropies of the reactants, and then we're done. And the entropies are going to be extensive. You know the difference between an extensive and an intensive property. Okay. What's an extensive property? What's an intensive property? This is back from chapter 1. You don't remember? All right, extensive means it depends on the amount, like volume. Volume is an extensive property. Density, however, is an intensive property because density does not depend on the amount. Energy always is an extensive property, unless you normalize it like this, kilojoules per mole, right? But if you have 2 moles, you're going to have twice as much energy, right? 3 moles, 3 times as much energy. So energy is always extensive. And entropy is the same. Entropy, depends on the amount. If you have 2 moles, you're going to have actually twice the entropy than 1 mole. And so we have to, when we do our delta S calculations, we have to pay attention to how much we have. Now, the units are kind of interesting. Look at the units here. It's joules, which is energy. And so, yeah, joules per mole per Kelvin. And so entropy is in units of energy here. But, it's orders make to smaller. This is kilojoules, we're looking at joules. So the entropies are smaller in number. Okay, now entropy is a measure of disorder. And so I talked about something. If you look at the Boltzmann equation, what's the lowest entropy that's possible? Well, the number of ways is 1. If the number of ways is 1, then the absolute entropy is 0. So 0 means it's perfectly ordered, right? 0 means that, in fact, they call this the third law of thermodynamics. The entropy at 0 Kelvin for a perfect crystal should be, the entropy, this is CP, sorry. The entropy is going to be, actually, this isn't 0. This doesn't have to be 0 here. The entropy is going to be 0. So if we look at the entropy curve is going to look like this. Oops, I made a mistake, sorry. This is not, shoot, sorry about this. This goes down. The heat capacity of the gas is comparable to the solid. The heat capacity, this is for water. The entropy curve looks like this. Since we're integrating the area, it's going to jump. Even though the heat capacity drops down, the total area is going to go up. And so this is why, gaseous water has a higher entropy than liquid. Liquid has a higher entropy than solid. But the entropy here at 0 is 0. The entropy here at 0 is 0. This is called the third law of thermodynamics. Do you know what the first law of thermodynamics is? What's the first law of thermodynamics? I heard. Yeah, energy is neither created nor destroyed. Energy is conserved. And so the third law of thermodynamics says that the entropy of a perfect crystal at 0 Kelvin is 0. That's as perfect as you can get, right? Perfectly ordered as you can get. And so I talked about that yesterday, but I didn't give it the name, the third law of thermodynamics. What's the third law? You might be asking, what's the second law? Well, we haven't gotten to the second law of thermodynamics yet.
Okay, why are the units of S and CP the same?
They're essentially the same, because it's just integrating the area. It's going to be the same. This is the molar heat capacity. They're related, but they aren't exactly the same thing. One is like the total area under the CP curve, although you'd think, okay, the other is just the CP. And so that's good, but I wouldn't worry about that just yet. Here. It kind of makes sense because if something has a high entropy, then you would expect it to have a fairly high heat capacity. So let's take a look at this. This has a fairly high entropy, 490. It has a fairly high heat capacity, which means that heat capacity is the ability to absorb energy. That means it has a lot of what? Something that has a high heat capacity versus something that has a low heat capacity. What's the difference? Something with a high heat capacity has a lot of, or not internal energy, a lot of yeah, you could say that, but a lot of degrees of freedom means what in terms of physical characteristics of the material? Yeah, lots of ways it can move. There are a lot of ways it can absorb energy, right? There's a lot of ways it can absorb energy means there's a lot of microstates. You know, it can vibrate like this or it can vibrate like that. The atoms can be different position, right? That kind of stuff. And so we're thinking about that. And so this is why you can see the relationship between, you know, as the heat capacity goes up, obviously the entropy should be. But then it's a little bit tricky because here somebody might ask you, the heat capacity of gaseous water is quite low. Right? The heat capacity of gaseous water is quite low, therefore should it have a lower entropy than liquid water? This is the confusing relationship here between heat capacity and let's say entropy. So this is one of the tricks, I mean not tricks, but one of the traps you can get stuck in. So liquid water has a higher heat capacity. Gaseous water has a lower heat capacity. Therefore, liquid water has a higher entropy. True or false? False. Why? Well, if there are more ways, you know, shouldn't it? If there are more ways liquid water can absorb the energy, shouldn't it have a higher entropy than gaseous? Gaseous is just translational. There's vibrational and rotational too, but you know, it's tricky conceptually because you know, it's this area under the, you know, and so when you accumulate the area here, then, so what does that mean in terms of physical sense? Well, for right now, you know, these are questions you can answer when you get to more advanced thermodynamics or think about, you know. For right now, I don't want to spend a lot of time thinking about the conceptual stuff. A lot of people, what they do with thermodynamics is they just do the calculations. The calculations are easy because you have the equation, you have your calculator, you have the number, you just punch it in, right? You don't need to understand it, correct? The thermodynamics is one of those subjects that are conceptually difficult to understand, and it's better to understand it. And so we're just taking it a little bits and pieces. We aren't going to go full bore into it. This is why I'm skipping some stuff, you know. It's just related to heat capacity, so okay, we can get absolute entropies. So what can we do with the absolute entropies? Well, once we have the absolute entropies, we can use those in calculations. But here you have to understand something, because when you look at the absolute entropies, what do you see? It's weird. There are some that are what? Negative. So what the heck is a negative? Does that mean it's even more perfect than a perfect crystal? What does a negative mean in entropy? Well, then, no, it doesn't mean it's unstable, because what is this? Aluminum 3 plus is unstable? What's that? Is it going to disintegrate in some nuclear reaction and aluminum 3 plus is totally unstable? AQ? No, aluminum 3 plus must be highly ordered. I mean, there must be some micro machine or something like that inside aluminum 3 plus that keeps the order, keeps everything well ordered. Is that it? And so you're going to have to explain this. Why do we have a negative entropy? And the thing is, you should already know Appendix D. What's weird about Appendix D? Somebody tell me what you learned in Chem 1A that's odd about Appendix D. Any of you guys remember? Remember we talked about temperature. Is it possible to have a negative temperature?
Yes.
How can you go below 0 Kelvin? Isn't 0 Kelvin the lowest temperature you can have?
Yes.
Then how can you get a negative Kelvin? Well, it's because I didn't ask you if you had a negative Kelvin. I just asked you if you have a negative temperature. Is it possible to have a negative temperature? Yeah, but it's on a different scale, right? Either Fahrenheit or Celsius, right? Then we could have a negative temperature. Is it possible to have a negative Kelvin temperature? No, that's impossible. And so absolute entropies have 0 as the 0 point, right? This is the lowest you can have, is 0 entropy, right? And so this must be a typo.
Typo!
It's possible because this book, books, all books have errors. I haven't found a book that doesn't have.
Is there another?
Is there no? I don't see any other negatives here. That's got to be a typo. Oh. In fact, there are a lot of negatives in here.
Are there all typos?
I think so. A lot of negatives.
Wait, what's the other? It does say it's relative to.
Yeah, do you see the pattern? Scott saw the pattern. What's going on with all the negatives? All the negatives are associated with not just any ion.
Metal transition.
No, not just transition metal. With, okay, keep looking. Keep looking. Well, let me take that back. Maybe there's no other pattern. They're all ions. Did you guys learn something about Appendix D with delta H? Okay, let me ask you this. This is something you should have learned in Chem 1A, but you probably forgot. H plus has a delta H of formation of 0. H2 has a delta H of formation of 0. How's that possible? How is that possible? H2 is possible because the delta H of formation is the formation of H2 from the element H2. Well, if we form 1 mole of H2 from 1 mole of H2, was there any energy change? No. But if we form 1 mole of H plus AQ from the element in the standard state, we're going from 1/2 H2 gas to 1 mole of H plus AQ. You're going to tell me that the energy involved in this is 0? This causes 0 energy or releases 0 energy? Is that true?
No.
No, it's false, right? And so this is false. But why is it 0? But, this is why I wanted you to review chapter 7, so I wouldn't have to spend any time talking about chapter 7. I don't want to spend any time talking about chapter 7. What's that?
Isn't it like those values are relative to the values of something else? It says at the top.
Well, let me give you a hint. Maybe this hint will spur your memory. HCl. Remember HCl. Hydrochloric acid. Good. Your memory is coming back.
Is it the formation of H plus from HCl?
All right. Well, it looks like I'll have to review this, right? Unless
No, you got
it doesn't click at all.
No, it's not.
Bummer. All right. Why I say HCl? Okay, HCl8Q has a delta H formation of minus 167.2. And so if we form 1 mole of HClAQ from the elements, then the energy involved in this is minus 167. And we could measure this, right, using calorimetry or whatever else. Just use calorimetry. Or we could use Hess's law to figure it out or whatever. Some calculation. It's exothermic, right. All right, when we form HCl, what are we forming? We're forming H plus AQ and Cl minus AQ, because HCl is a strong electrolyte. It's not going to be molecules, it's going to be ions. And so the question comes out, how much of this minus 167.2 is due to the H plus, and how much of it is due to the chloride? Is it 50% of the energy is involved in the formation of H plus, and the other 50% is involved in the formation of chloride? No, it's not a 50-50 split. Well, maybe is it 80-20? 80%, 20% of the energy? What is it? What it is we'd have to do some theoretical calculations, figure it out, right? Because can you form, you know what? I just want to form the H plus. I don't want to form any of the chloride. Is it possible to do that? No, unfortunately it's impossible. And so what we have here is we have two unknowns, one equation, and we can't think of another equation. When you have two unknowns and one equation, you could either give up and say, okay, I can't solve it, forget it, right? Or you could make an assumption. What do you think people will do?
Assumption.
Well, a lot of people will give up, but some people will say, okay, I'm going to make an assumption. I'm going to assume what? I'm going to assume that there's zero energy for the H plus. And so we'll say the delta H of formation of H plus is equal to 0. And therefore, the delta H of formation, we're going to assume a 0, 100% split. And so that means 100% of the energy is due to chloride. And so all delta H of formation of chloride is going to be equal to minus 167.2.
Which is what it is.
Yeah, if you go to chlorine or chloride thing, if you go to chloride, you'll see that, what is the delta H of formation of chloride?
Negative 167.2.
Negative 167.2. So 100% of the energy goes to chloride, right?
Uh-huh. So that's why H plus is 0.
That's why H plus is 0. But you think, oh man, that's going to be a huge error, isn't that? That's a huge error. But it's not a huge error, because it's a huge error one way for H plus, and it's a huge error the opposite way for chloride, right? But you cannot form a cation without an anion. And so all the cations are going to be off by one direction. All the anions are going to be off by another direction. And so whenever you take a cation and add it to an anion, those errors cancel each other out. And so it's systematic error off in one, systematic error off in the other, but we don't form one without the other, and so those systematic errors will offset. And the other thing is, we can't compare. You don't compare the energies of an anion with the energies of a cation with the energies of a neutral compound. And so essentially, this is what I say in Chem 1A, that this table is a table that has the Fahrenheit, the Celsius, and the Kelvin temperatures all in the same column. And you go, wow, why don't they just make 3 separate tables? Well, that's a good question. Why don't they make 3 separate tables? You know, separate them all out, and that way people don't get them mixed up. And they figure that it's not necessary, because if you can't deal with this, then maybe it's, I don't know. Maybe, I'm thinking why Petrucci does this. Well, maybe the answer is this. A lot of people will never know. They'll never know this. And they don't care, because all they have to do is take the number from here, put it in the equation, and it works magically, right? And then the people that want to know, well, they'll be able to figure it out, because this is not that bad, you know. And so essentially this is what happened. What has a higher entropy? Solid aluminum or aluminum 3+?
Solid.
Solid aluminum has a higher entropy than aluminum 3+ because?
More disordered.
So a nice crystal of aluminum is more disordered than aluminum 3+ ions
Oh, no.
in solution.
No.
But
So it's the absolute value. What is it?
it's not the absolute value of the entropy. This is the same thing as if I asked you this. What's a higher temperature? What's a higher temperature? 10 degrees Fahrenheit or -1 degree Celsius?
You can't compare.
Well, you go, oh, 10 degrees Fahrenheit's a higher temperature because it's a bigger number. 10 is greater than -1, right? But that's wrong, because 10 degrees Fahrenheit is a colder temperature than -1 degree. You can't compare the two, right? You can't compare the two because they're on different scales and they have a different reference point. The 0 point is different, right? And so the same thing here. The 0 here is the absolute 0 of entropy. The 0 here is what, okay, if you know delta H, what's the 0 point here? This is -321.7, so 0 must be what? Zero must be, this is what we call an arbitrary zero. For example, Celsius has the arbitrary zero of the freezing point of water. Fahrenheit has the arbitrary zero of, actually, what is the zero? The coldest winter day, something like that, right? Isn't that how 0 Fahrenheit was defined? How is 0 Fahrenheit defined? The average coldest winter day? No, actually 0 Fahrenheit would be extremely cold. Oh, I would think it would be the coldest winter day in England, in Fahrenheit's neighborhood, probably. But anyway, those are arbitrary zeros. So we're dealing with 3 different entropies here. One that's referenced to absolute, which would be all the compounds and elements. One that's referenced to the cations, and then one that's referenced to the anion.
Temperature of a solution of brine.
Oh, temperature of a solution of brine, but that
From water and sand.
brine can have any temperature.
I guess that.
There must be the freezing point of brine, and then it has to be a certain concentration, maybe a saturated solution of brine, something like that.
What's brine?
Salt and water.
All right, so can you tell me what the 0 point for the cations will be? Epsom salt? Okay.
No, brine made from equal parts of ice and salt.
Oh, okay, ice and salt equal, okay. Then that makes sense.
And then the best estimate.
You know, that's the first time I always guessed it was the coldest winter day. That's totally wrong. I had no idea. So we know the absolute entropy, right? But what is about these relative entropies? What's the 0 point for the cations? Tell me.
Would be the solid.
That's not the solid state. It's the same. You know, chemists they don't want too many different reference points. And so what was the 0 point over here?
0 Celsius.
What was the arbitrary? This is arbitrary. This is, you know, arbitrary because it's just defined. Somebody just picked this and said, I'm going to call this
R0.
0, and then we'll measure everything else. So lithium ion is going to be different and whatever else, because if you make lithium chloride, then yeah, that's going to be different. We know the delta H formation of chloride. Now we just got to figure out lithium, and this is going to be the difference, right? And so this is the arbitrary 0. Well, don't you want to keep the same? Like, if you're going to do brine, you might as well always make it brine. Otherwise, you say, okay, it's brine for this, and it's going to be a saltpeter for that. You know, it's too much hassle. And so what do you think the arbitrary 0 for the entropy is? Not delta H of formation, we're talking the absolute entropy. The absolute entropy of, hopefully this will scroll down. Do you see it? The absolute entropy of 1 mole of H plus AQ, and the molarity is fixed because under standard thermodynamic conditions from chapter 7, what are standard thermodynamic conditions from chapter 7?
0 Celsius.
Not 0 Celsius, that's for gases, chapter 6.
1 atmosphere pressure. 1 atmosphere pressure and 25 degrees Celsius.
No, that's wrong.
25 degrees Celsius.
1 molar solutions and
Oh.
1 atmosphere or 1 bar gases. That's standard thermodynamic conditions. We need the molarity fixed because that's going to change its reactivity. And so forming 1 mole of 1 molar H plus, okay, gives us a delta H formation of 0. But what is a solution of 1 molar H plus? Is a solution of 1 molar H plus perfectly ordered?
No.
Then why does it have 0 entropy?
Not arbitrary 0. This is an assumption.
Just, you know, just start this.
Measurements or something else.
The assumption based on existing
It's what?
The assumption based on existing
No, not the assumption. So there's no assumption here. Why is the entropy of 1 molar H plus 0? Well, no, it's not assumed. Somebody else did something. Somebody else defined it. It's an arbitrary definition. Somebody arbitrarily called it 0. Because if you form H plus, then that means all the entropy must be in chloride. And so when we look at this reaction, let's say we're looking at something like this reaction here or something, or actually this is not a delta H, this is just absolute entropy. And so let's figure out the entropies for this. And so I got 1/2 H2 gas. This is how we do an entropy calculation, plus 1/2 chlorine. This is going to go to H plus AQ plus Cl minus AQ. And so all I do is I figure out the entropy of the products. Well, H plus is easy. The entropy of H plus is, and this is under standard conditions. Standard conditions tells me that these gases must be at these gases must be at 1 bar or 1 atmosphere. Well, I have a 1/2 mole here, so does that mean it's a 1/2 bar or 1/2 an atmosphere? No, this has nothing to do with it. These are just the ratio in which it reacts. These aren't the pressures, these aren't the concentrations, these aren't the volumes. And so I'm going to have 1 bar this, 1 bar that, let's say. We'll talk bars. We'll talk bars. And that standard means that this is going to be at, well, this is going to be what? 1 molar. And that standard means chloride is going to be at, and does that standard mean that this is going to be at 25 degrees C? No. No, the standard does not mean it's at 25 degrees C. So what temperature is it? Well, we have to look it up because that little standard symbol doesn't tell us. And if we look it up, we would see that it's at 298 Kelvin, which is 25 degrees C. And so we have to specify the temperature, but this little standard this will tell us. And so this is 0 joules per Kelvin mole, or joules per mole Kelvin. Okay, what's chloride then? Well, actually, since we're on H's, let me do H2. H2 is 130.7, but I have 1/2 a mole, so that's 1/2, 130.7 joules per mole Kelvin. So I should use dimensional analysis. 1/2 mole. This is going to be 1 mole. Okay. So let's go to chlorine. Okay, that's for the enthalpy information, but we want this. For chloride, it's 56.5. 56.5 joules per mole Kelvin, and I have 1 mole of that. All right, now look at this. A solution of HCl has a total entropy of 56.5. This HCl consists of the H plus and the Cl minus. The problem is we don't know, out of this 56.5, we don't know how much of that entropy is H plus, how much is chloride. So what they did was, there's 2 unknowns, 1 equation, no second equation, so they're just going to arbitrarily define one of the variables as 0, otherwise we go nowhere. And it turns out that it's no big deal because it's just a systematic error that will cancel out. Then it cancels out because I add this and I get the right entropy, 56.5. And everything's going to be offset, so no big deal. Now, what is the absolute entropy of chlorine? It's a gas, so it's going to be higher, 223.1. So we have 1/2 mole of chlorine at 223.1 joules per mole Kelvin. So the moles cancel out, and we just end up with joules per Kelvin. So let's figure out what is the entropy change. And so delta S is just S final minus S initial. And so S final is 56.5 minus S initial. S initial is 223 plus 130 is 353.8. 353.8. Units here will be joules per Kelvin. And so the entropy change here is minus something, minus 2.
97.3.
Thanks. Joules per Kelvin. So the entropy went down. Entropy went down because gases have pretty high entropy. You know, there's a lot of empty space, a lot of positions. Although aqueous solutions are going to have lower entropy, they're still fairly high. Oh, never mind. I forgot. Yeah, I got to do 1/2. Let's do it again. Divided by 2.
Excuse me, what's the purpose for delta S?
The purpose of delta S is just to figure out the entropy change quantitatively. Qualitatively, we would have said delta S is probably less than 0 because, you know, we're going from gas to liquid or aqueous. So we're going.
What are you trying to do? You're trying to compare the entropies? You're trying to compare the entropies?
No, not yet. All we're doing is we're calculating the entropy. What was it, minus 120? 0.4. Thanks. Joules per Kelvin. And so we lost some entropy, so it's going from less order to more order. Well, that's not favorable, right? Not favorable, but we don't know what the energy is. So calculating entropies is easy. So using these numbers, you don't even have to know what the numbers mean, but using the numbers is easy, right?
Yes.
Anybody could do that. And so you don't even have to go to school to use this delta S, right? And use the table.
Yeah.
So you might be wasting your time here, you know. But the problem is anybody can do it. Therefore, you know, this stuff can be, you know, outsourced easily. You know, just have somebody buy, you know, they buy them a calculator and they can do it, right? But the stuff that can't be outsourced is telling somebody, you know, the numbers, you know, like this. Do you think this is easy to understand, this table? Maybe they made it purposely complicated so that it can't be outsourced so easily. Well, it's not complicated because everything's there contained. And so the important thing is not punching the numbers into a calculator. The important thing is at least understanding a little bit about the numbers, right? Like the delta H. You know, if you didn't know anything about the delta H's, then you know the calculation you did with the delta H's of formation? That's nothing special. Delta H of you know, reaction equals the sum of the delta H of the formation of the products minus. Anybody could do that. You know, so you got to understand a little bit more, you know, about these numbers, always. Otherwise, well, anyway, going back to this, let's look at some of these numbers. So let's go back to this. What do you think has a higher entropy? Aluminum solid or aluminum AQ?
AQ?
Yeah, even though the number is
Negative.
and very large.
Large.
Yeah, okay, so that's the first trick. We can compare. What do you think has a higher entropy? Aluminum 3 plus AQ or barium 2 plus AQ? Aluminum 3 plus AQ or barium 2 plus AQ? Which one has a higher entropy?
Entropy?
Entropy.
Barium.
Barium 2 plus AQ. Barium 2 plus AQ has a higher entropy. It has a much higher entropy. Here we can, this is a fair comparison because both of these are cations. So, you know, if you compare Celsius temperatures, then no problem. So this is like comparing 2 Celsius temperatures, right?
Yes.
Versus this, what has a higher entropy? Aluminum solid or aluminum chloride?
Chloride.
Aluminum chloride.
Those are on the same
Why?
scale. They're on the same scale. They're both.
Well, the
solid
first thing
molecule.
we're doing is we're just learning how to use the numbers right now. And then we're going to look for our overall pattern in the numbers. All right. And so the comparison, and then we can compare anions directly, right? So for example, we can compare bromide 82.4 with chloride 56.5. Which one has a higher entropy?
Bromide.
Bromide. And so comparing anions with anions, no problem. Cations with cations, no problem. And elements and compounds with other elements and compounds, that's no problem.
How about a solid and
Yeah,
aqueous?
they'd be the same state.
No, they don't have to be the same state. And so we can compare something like liquid. Let's compare. Let's see.
Let's go mercury.
Let's go with water. Or, because water has 3 states, right? What are the 3 states of water? Solid, liquid, gas. So here we can compare it here. H2O solid. Oh, sorry. We'll just use liquid gas. H2O liquid, 6991. H2O gas, 188.8. Okay, so what you should do is you should look at these numbers and look for a pattern. I'm not going to go and look for the pattern for you. Let me just tell you, but you should do this yourself. Solids are going to have an entropy from 0 to about 100. And so there are going to be solids with higher entropies than 100. Those are the outliers. So for example, here, if we look, okay, from 0 to 100, about solids. So this one's about 110, but this one is 490. And so 490 means, wow, that has a much higher, well, actually, that's not a solid, that's a gas. Oh, which one? Here.
That's the same, right?
239. That's kind of a high entropy for a solid. So that's kind of an outlier. So this is a more disordered solid. There's a more disordered solid because it's got to be maybe the sulfate, vibrating, that kind of stuff. Or some solids have a very high entropy because inside the solid itself, inside the lattice, the ions can actually rotate. And that bumps up the entropy quite a lot.
Okay, there are different crystal networks. Some crystal networks are disordered, like in iodine solid.
Yeah, molecular solids are going to have maybe a higher entropy, iodine solid. Let's see what iodine solid is, if we want to look at this. A, B, C, D, E, F, G, H, I. Should be this one. If we look at iodine solid, 116, is that unusually disordered? No. It's not. I mean, okay, it's on the higher end, 0 to 100 or so. Elements are going to have low entropies because, elements, they just have a single atom. There's no molecule, there's no vibrations, this kind of thing. Iodine is going to have vibrations, a molecular solid, plus the molecules themselves will vibrate, and, there could be some shaking in there, like partial rotations in the molecular solid. So it's going to have a higher entropy. You got iron like this. It's, all the iron atoms are in this is a body-centered cubic, and a body-centered cubic lattice. There's not much you can do. The same thing with aluminum. What's especially ordered, like diamond? What do you think the entropy of diamond is? Super high. Yeah. Let's see what the entropy of diamond is. Wow. Look at that entropy. 238. And so what do? When you get a table like this, you look, what is the lowest entropy of a solid? What's the highest entropy of a solid?
Isn't that really low on the solid scale?
I know. I mean, did I say it's going to be high or did I say it's going to be low?
No, it should be low because
No, sorry. No.
Super ordered.
Sorry. It's super ordered. Diamond is super ordered, so you expect a very low entropy for diamond.
Almost no.
Well, there's vibrations, but the way they vibrate, there aren't too many vibrational modes. In fact, for graphite too. So what you want to do is you want to look, okay, solids, what are the range of entropies, right? What's kind of the average? What is kind of the outlier? So this is what I'm going to tell you. But when somebody tells you, it's easy to forget. The best thing is if you do it yourself, and then you'll remember it much more because you put in the work in doing it, right? And so That's why I try not to tell you. I try to have you do it yourself. Well, anyway, but I'm going to tell you this. Liquids are going to be about 100 to 200, typically, right? 100 to 200. But there are going to be some outliers. One outlier is water. Liquid water has a fairly low entropy, like 80, what was it, 88 or 68 or something. Liquid water has a fairly low entropy because of the hydrogen bonding interactions. It's strong, keeping it pretty well ordered. So. Aluminum 3 plus. Aluminum 3 plus has a fairly low entropy. I mean, minus 323. That was pretty low, wasn't that? Minus 321. That's pretty low entropy. Why? Why is aluminum 3 plus at a minus 321 and barium 2 plus is a 9.6? Huge difference there in entropy, right?
Why?
And well, aluminum 3 plus is quite a bit more order because it forms a hexaaqua, right? Hexaaqua complex in water, and so there's going to be considerable order in the ion itself. Let's say compared to barium 2 plus, which really is just going to be ions and translating this stuff, so it could be more disordered. And so there's more structure. This is more constrained because you got those 6 waters and the octahedral, right? Configuration, this kind of thing.
Okay, so why does aluminum solid have a lower entropy than Al3 plus aqueous?
Because aluminum solid is an aluminum. I think is body-centered cubic also, and so aluminum solid is going to be a nice, lattice. It's 8 coordinate in a crystal, and so you get nice little crystals of aluminum, right? And so it's going to be ordered. Whereas Al3 plus, it can be anywhere in the liquid, and so when we talk about entropy, we're looking at how many different positions can each atom be in. That kind of thing, in space, in 3-dimensional space. That's a lot, This is why we aren't going to count the number of ways. If you took 1 mole of hydrogen in 22.4, 22.4 is 0 degrees C. What's the molar volume of the gas at room temperature? Everybody knows 22.4, but it's a complete waste of time because how many reactions do we do at 0 degrees C? No. How many reactions do we do at 25 degrees C? Practically all of them that we do. And do you know the molar volume of the gas at 25 degrees C?
No.
No, that's a disappointment because you should. It's much more useful number to know. 24.5, Scott knows. That's good. 24.5, right? And so if you have, well, that's a disappointment that I have with the book because the book emphasizes STP, but I guess it's useful if you're making comparisons with STP, but,
What are some of the values of those dashes that we're looking at today?
I don't know. That's a good question.
Because they dissolve.
You can't compare this to that.
Form the aluminum 3 aqueous.
What is
Just refer to that.
Yeah, this one,
Which two can't you compare?
I see a lot of hydroxides.
yeah, this could be, there could be several reasons for that data is missing. The hydroxides are very difficult sometimes to deal with because, and it depends on who does it, but it could be because hydroxides, you have to work in an air-free environment if you really want to do hydroxides properly. Because hydroxides, like for example, sodium hydroxide will decompose over time. Do you know how sodium hydroxide decomposes over time? It really doesn't decompose, it reacts over time. It reacts with CO2. It forms sodium carbonate in water. This is a acid-base reaction, Lewis acid-base reaction. And so most in fact, they use lithium hydroxide on like the space shuttle or whatever else to scrub out the CO2 from the air because if the CO2 concentration gets too high. And so it could be because there's no data for it, But, you know, this table's old, so there could be data out there, it's just not reliable. Sometimes they'll see data, different numbers, and the numbers are totally different, and so which one do you pick? Do you average the two, if they're totally different? And so a lot of this is experimental data, and so maybe there just isn't good, reliable data for this, but you probably can find it in the literature if you look, you know, because aluminum hydroxide shouldn't be a problem. Mhm. Right,
And it has some version of disorder.
right. But that's a good question, and that I don't know why, because there's no footnote on that, huh?
You said you can't compare it between what and what?
Or when you're comparing it, to compare the same, that's all.
Yeah, exactly.
The same what, Celsius?
Yeah, Celsius, if you compare temperatures, if somebody said, what's a higher temperature, -10 or 5? What's a higher temperature? If somebody asks you, what's a higher temperature, -10 or 5, what would you say?
On what scale?
Yeah, on what scale? Right. You would automatically assume they're talking about the same scale. You know why? You know, you would be upset with them if they weren't talking about the same scale, because you're trying to trick me. It's a cheap trick, right?
Mm-hmm.
And it's not a fair question. If somebody said, what's a higher temperature? You know, 5 degrees C or -10, and you said, oh, 5, of course it's 5, and they said, nah, wrong, it's -10, you know, I fooled you, ha ha ha. Well, that's what this table is going to do to you. This table is going to do that. This table is going to say, what's a higher entropy? Ha, you got that wrong.
Next one.
And you go, why are you doing this to me? And so this is why I asked, why didn't they separate it into 3 tables? So I've been thinking about that, or you know, and so the only reason I can come up with is one, they don't want to talk about it, right? One, or they do talk about it. It's down there. They talk about it in chapter 7. There's a paragraph about it, you know. But basically, watch out. You know, this table is trying to play a cheap trick on you. Okay. And so that's why you can only compare cations with cations, and anions with anions, and elements and compounds with other elements and compounds. That's it.
You can't compare cations and anions?
No, don't
They're on
compare
different
cations
scales.
with anions because they're on a different scale. Okay. Right. You know, anyway, you go through this, you look, okay, between 100 and 200 liquids, and then greater than 200, we have
Sure, gas.
gases, right? All right, there are going to be, you know, outliers in both. So one of the outliers is going to be H2O liquid. H2O liquid has a fairly low entropy for liquid. Why? Because of hydrogen bond. But when we look at it, are there liquids with even lower entropy?
Then water.
Look at the entropy of water, 69.91. That's pretty low, isn't that? Would you say? Yeah, that's pretty low entropy. You know, and so what you want to do is you kind of want to get a feel. H2SO4 has a really low entropy.
Why?
Cute, because there's got to be constraints, you know, order to it. And it could be, you know, the sulfates are highly charged, you know, -2, etc. And so there are things. Look at H2SO4 liquid, wow, 56.9. And so this shows the aqueous state. The aqueous state, you know, because aqueous state we could either have complex formation or hydration. And so that's going to increase the constraints, which decreases the disorder in the system. But anyway, you want to get a kind of a feel for this number. So what we do is we can just guesstimate. If you're going from a solid to a liquid, what's the delta S approximately? Delta S is approximately 100, right? Yeah. We're not going to go 50 to, the range is going to be huge, right? It's just kind of a guesstimate. If you go from a liquid to gas, what's delta S? About 100, right? If you go from a solid to a gas, it's going to be about
200.
200. Well, you know, that's just a ballpark, right? Ballpark guesstimate. But actually calculating it is so easy. Why even bother with the ballpark? So let's see, we're going from gas to kind of a liquid phase, aqueous phase.
Should be around 100.
It was around 100, right? About 100.
Uh-huh.
Give or take.
Give or take. Well, you know what rules are compared to laws?
Generalities.
What's the difference between a rule and a law, would you say?
I would say one, you can break it if you want to, and when you break it, you get in trouble.
Yeah, hopefully rules are going to have a heck of a lot more exceptions.
That's a good
Yeah,
one. Yeah.
probably a heck of a lot more exceptions. So solubility rules, not the solubility laws, right? All right, let's you know, I don't want to talk about this rule at all. Just thinking, rather skip this rule entirely and just say this, but oh, I can't even see it. Can't see it. This is weird. I wonder why the scroll bar, does somebody know why the scroll bar disappears when I resize the window?
The only thing it could be is in tools. Maybe like one of your drop down windows isn't there. But lock the toolbar.
Try to use a little.
Try to cancel that box. Excuse me, I'm trying to cancel that,
Well, anyway,
that box.
there's something called Troughton's rule. Troughton's rule states that for many liquids at their normal boiling points, the standard molar entropy of vaporization. So we vaporize a liquid, so we're going from a liquid to a gas. So Troughton's rule says that the delta S is about
87.
87.
Kelvin.
Do you want to memorize that? Did you see do you know, whenever we look at numbers, we kind of look for the average and we kind of look for the spread, you know? And the spread is something we always think about, you know? And so here, Troughton's rule is saying it's 87, but what's the spread on that? It's huge. The spread is big, right? And so how is that really worth memorizing? Not really. But this is a pattern that Troughton noticed. This works for organics pretty well. And so for organics, they kind of cluster here. But if you do water, forget it. If you do anything else with hydrogen bonding, forget it, because it's quite a bit different. Water is going to have a much larger entropy change because the liquid phase is much more ordered. The gaseous phase, all the gaseous phases are quite a bit disordered, right?
Yes.
And so there are a lot of exceptions. So Troughton's rule works okay for organics, but for other ones it doesn't. So, you know, on the one hand, I say, it's not even worth it. Remembering,
Well, why H2SO4 has such a low entropy of 20.1?
That's a good question. And so you'd have to look, you know, what about the structure of H2SO4AQ gives it such a low entropy? And so there's got to be some, you know, pairing interactions. There's got to be, you know, some hydration, et cetera, that, you know, and when you build these structures, it's not like the randoms can be, you know, if you got a sulfate ion here, it's not that the waters can be any orientation. I mean, this is a high charge, so what end of the water is going to point to this?
Positive side.
The positive side of water is going to point to this. Well, now that's a constraint. That's more order. Because, you know, if this were truly disordered, then any part of the water can point to this, right? And then once you start doing that, well, this has got to have a really well-ordered hydration sphere
Around it, yeah.
around it. It's just like aluminum. Aluminum is so, you know, ordered, it's going to have an octahedral. And not only that, these are going to be bonded these aqua ligands are gonna be bonded to the aluminum.
Gives it a lot of order.
Yeah, and it's gonna give it a lot more order, because now this is well-ordered structure. Even though this whole thing is gonna be moving in water, right? But this whole thing is gonna be positively charged, which means even the surrounding water molecules are going to wanna point the negative end to this, which creates more order. And so all these things add up to, and I don't know why it's that specific number, because that's exceptionally low, but it's gotta be pretty well ordered, or pretty well constrained, all right? Well, let's continue on with the Troughton's rule. So there are exceptions there. You heard of it, but it's not going to be that useful, because unless you have an unknown, you know, then it might be useful. All right. So we can calculate our delta S's. Calculating delta S's is not that difficult. We have the data in Appendix D, and we just calculate it. But how do we use that? Well, now, once we have that number, we have this number here, and then we have our delta H. Our delta H is equal to minus 167 point whatever, kilojoules per mole. This is 1 mole, so it's just going to be kilojoules. And so how do I compare these two numbers? Okay, so my delta S, the entropy is going down. I don't want entropy to go down, I want entropy to go up. And so entropy going down says that's no good, that's no reaction. But the energy is going down, that says reaction. So we have this conflict. Remember, the conflict is one driving force says no reaction, the other driving force says reaction. So how do we compare the two? Well, I said, well, we need numbers. We can't just do this qualitatively. Now we have the numbers. Now how do I compare the numbers? And so which one wins out? Or is it going to be, which one's going to dominate, let's say? Will energy dominate, or will entropy dominate?
Entropy. Entropy.
Well, unfortunately, units aren't the same.
Oh, you can't compare that with the origin.
So how do I compare the two? Well, I guess I could pick a temperature. Well, I already know what the temperature has got to be. This data came from 25, so I could put 298 Kelvin. Get rid of that and multiply this by 298. So let's do that. Can somebody multiply that by 298? At 298 Kelvin.
35,879.2.
35,000. So this would be 35.8 kilojoules. So this is negative 35.8 kilojoules at 298. This is minus 167 kilojoules at 298. Which one wins?
Wait, okay. Wait, from joules to kilojoules, you're gonna go a factor of 1,000, right?
Yeah. So John said it was 35,800, so I just converted it in my head.
Okay.
It was 35,800. So now,
So delta H.
so yeah, it looks like delta H is, well, is it the winner?
No. It's delta S. Entropy.
Well, it looks like the entropy went down by 35.8 kilojoules, but the energy went down even farther. Entropy going down is not favorable, right?
Mm-hmm.
But energy going down is favorable. And so it looks like the energy was more than enough to compensate for the unfavorable energy decrease in entropy. Does it look like that? And so it turns out there is a reaction here. The reaction won out.
How rough, what's good? As long as it's bigger, or does it have to be bigger significantly?
How no?
But like if you're comparing the two, if it was like 35.8, 36.
All right, there's going to be two ways we do this. All right, this, is this correct? Am I thinking here? You know, that's it. And so, yeah, is it fair to compare entropy with energy directly? Is that fair? You know, and so what people did was they started looking. It turns out that, you know what, this is correct. This is correct. But it turns out that people were looking for something in common. You know, whether the energy goes up or down, what do all spontaneous, you know, spontaneous just means it has a driving force. Reactions and processes. Okay, it turns out all spontaneous reactions and processes, whether the energy goes up or down or entropy goes up or down, all of them have one thing in common. Not the temperature. What they have in common is that the entropy change of the universe increases. Entropy change of the universe. This is called the second law of thermodynamics. It turns out that this works, but you know, how's that related to this? We'll see how it's related to this.
Okay, why does reaction win out? Negative 35 is much bigger than negative 167.
Okay, negative 35, is it greater than or is it less than negative 167?
It's greater than.
No idea that line you're talking about. Yeah, where's the top of the scale?
All right, unfortunately, Petrucci does this sometimes. Petrucci will say this, but when we deal with energy, let me ask you this. To your bank account, what's bigger? Minus $35 from your bank account or minus $167 from your bank account?
Minus 35.
Minus 35, okay. I'll give you a debt of minus $167 if you give me your debt of minus $35. And then you come out ahead? Or
No, negative 167.
yeah. This is bigger, right? Well, energy is the same way. You know, is there such thing as a negative $35 bill? Is there such thing as negative 35 kilojoules?
Yes.
No. There's no such thing as negative 35 kilojoules. It's
less than
negative just means the direction of change. Just like negative 35, there's no such thing as a negative $35 bill. The negative just is the direction of exchange, right?
Direction of exchange.
And so when you said negative 35 is bigger, no, negative 167 is way bigger. Because negative 167 is an exchange of 167 kilojoules. Negative 35 is an exchange of 35 kilojoules. This is a much bigger energy exchange than this. You got it? Okay, so energy is like money. There's no such thing as negative energy. Well, negative energy in our context, there's no such thing as negative energy. And so we have this delta S of the universe. Well, is this very useful? Is that very helpful? No, because it's too much. The universe, I mean, how are you going to measure everything happening in the universe? Is that even possible? No, it's impossible. So delta S of the universe is, we divide the universe into two things from chapter 7. The universe is subdivided into what? The universe is going to be subdivided into the system and surroundings. Delta S to the system, this is easy. It's easy because this is just the reaction. We just got delta S of the reaction, you know, or delta S of the process. We just use appendix D. The surroundings, what do the surroundings consist of? Well, the systems are reaction or process. The surroundings will be everything else. Right? This is hard. But, actually, you know what? I wrote that equation. Can you correct this equation? It's not the absolute, it's delta S is equal to Q reversible over T.
Where is it?
Yeah, I just and so here, this is what we're going to do. I don't know what I was thinking. Yeah, this is the equation here. Delta S is Q reversible over T. And so we're going to leave this as is because that's easy. But delta S of the surroundings, so delta S of the surroundings is equal to Q, I'm going to get rid of this reversible. I'm just going to call it Q of the surroundings over T. Okay. But any heat that's absorbed or released by the surroundings must have come from the system, because the first law of thermodynamics, remember the first law, there's lots of ways of saying the first law, but one way of saying the first law is that Q of the system is equal to minus Q of the surroundings. And so what we could do is we could do this, that Q of the surroundings is equal to minus Q of the system over T. That's the first law of thermodynamics. Now, how do we determine Q? Well, Q is a path-dependent function. It's not a state function. We want Q to be a state function. How do we make Q a state function? We make it into delta H. The definition of delta H is equal to Q sub P with only P delta V work done. And so, in other words, what we do is we use the definition of delta H. Why I wanted to use it. And so, minus Q of the system is, well, definition of delta H is we just restrict it, constant pressure, P delta V work only. And so then if this is, well, this is going to be minus QP over T, and minus QP is, what am I doing? Yeah, that's right, is minus delta H, right? This is for QP of the system. And so this will be delta H of the system over T. So even though the surroundings seem like a horrendous thing to think about, the rest of the universe, it's not hard because the system is just going to dump heat into the surroundings or absorb heat from the surroundings. Well, that heat's, you know, coming from the rest of the universe. And so this is just going to simplify into delta S of the system, right, minus delta H of the system over T. Well, let's multiply both sides by T. If we multiply both sides by T, we get T delta S of the universe is equal to delta S of the system minus, T delta S of the system minus delta H of the system. All right? Then we're going to multiply by -1. So if we multiply by -1, that's t minus t delta s of the universe is equal to, so I'm going to flip these. So it's going to read delta H of the system minus t delta s of the system. And so I'm going to define this as delta G. So delta G is going to be defined as minus T delta S of the universe, which is equal to delta H of the system minus T delta S of the system. And so this is a new state function. It's called the change in the Gibbs free energy. Gibbs is a famous thermodynamicist. Change in Gibbs free energy, and G is called the Gibbs free energy.
So are you deriving the Gibbs energy equation?
Yeah. And so if this is a state function. State function is, it just depends on the initial and the final state. It doesn't depend on how it gets there. And so when we look at the Gibbs free energy, if the universe entropy increases, then the Gibbs free energy is negative. And so what this means is delta G less than 0 means that the delta S of the universe must have increased, that is greater than 0, therefore it's spontaneous. And so delta G less than 0, that is, we want a negative delta G, which means it's spontaneous. If delta G is equal to 0, then there's, we call equilibrium situation, there's no change. If delta G is greater than 0, then it's non-spontaneous. There should be no reaction, non-spontaneous. In fact, the reverse reaction should be spontaneous. And so delta G is going to compare. Compares the energy to the entropy. The entropy has got to be multiplied by the temperature. That's going to alter the entropy. And so our comparison was actually correct. What we're looking for is the energy dominant or the entropy dominant here. And so these are our two factors. So to have negative, we want this one. If this is negative and this is positive, then both terms are negative. A negative and a negative, that's going to make this even more negative. That means it's spontaneous. If the energy is if the energy is negative and the entropy is negative, we'll go negative. Do that? Yeah. And so this is favorable, that's unfavorable. And so this is what we call spontaneous at low temperature, non-spontaneous at high. And so it depends. At low temperature, it makes this unfavorable term smaller, and therefore the energy can dominate. If this is positive and positive, then the energy is unfavorable, but the entropy is favorable. And so this is what we call spontaneous at high temperature. There's a driving force, but non-spontaneous at low temperature. And if this were positive and negative, this is unfavorable, that's unfavorable. So this is non-spontaneous at all temperatures. This is spontaneous at all temperatures. And so here we can do a direct comparison between the two driving forces. But, one of the driving forces, we're talking about energy, and we'll talk about that more later. All right, I'll stop here. 2 minutes.